In this video, we're going to discuss inverse functions. This isn't necessarily a new class of functions like polynomial functions or rational functions. Instead, an inverse function, or maybe it's better to call it a function inverse, represents a new rule we can find in relation to a given function to be put to a very specific use. The word inverse relates to the verb invert, so a function's inverse inverts or flips the function itself. When you invert an image, all the light colors become dark and all the dark colors become light. And if you were to lay one image on top of the other, all of the colors would combine and you would be left with solid black. The image and its inverse cancel out one another. Functions and their inverses work the same way. They cancel each other out. We use inverses in algebra all the time when we solve equations. If we want to get rid of addition, we use subtraction. If we want to get rid of multiplication, we use division. And if we want to get rid of an exponent, we use a root. Now suppose we have a function that contains all three of these operations. Is there a way that we can cancel all of them at the same time? This is the purpose of the function inverse. It represents the sequence of operations that we would follow to cancel out the entire function rule so that we get back the variable completely isolated and unaltered. So we have two goals. The first is to determine whether or not two functions are inverses of one another, and the second is to take a given function and find its inverse, both algebraically and graphically. However, before we get to inverses, we need to define the term one-to-one. One-to-one is an adjective used to describe a function, just like we can describe a function as even or odd. As we already know, the requirement for a function is that each x corresponds to exactly one y. In other words, there's no repeating x or repeating input. A function, keep in mind it's already a function, we're assuming what we're starting with is a function. A function is one-to-one, which we abbreviate as 1-1, if each y corresponds to exactly one x. So a function is one-to-one if there is no repeating x or y. In other words, each input is matched to exactly one output, and that output only results from that one specific input. It's algebraic monogamy in a sense, no extra spouses on either side. Given the graph of a function, the function is one-to-one if it passes the horizontal line test. Remember, we had the vertical line test to determine whether or not something is a function. Well, if it's already a function and we want to determine if it's one-to-one, we apply the horizontal line test. This test works the same way as the vertical line test, but in this case, a function is one-to-one if each horizontal line only crosses the graph in one location. One-to-oneness is important to remember as we start to define inverses. So let's officially define inverse functions. So let f of x be a one-to-one function. So we're assuming that the function we're starting with is one-to-one. Typically we'll be told that it is, but if we're not told that it is, essentially we do need to verify that it is. So we have to make sure that for every input we put in, we get one output, and that output couldn't come from different inputs. So we're assuming we're starting with a one-to-one function. Then another function, which we're calling g of x, is the inverse, or the opposite of f of x, if two conditions hold. So the first condition is that f composed with g of x is identically equal to x. So in other words, if we take g of x and plug it into f, then we get x out. We also have to be able to do it in the other way, so g compose f of x also has to be identically equal to x. So if we take f of x and plug it into g, then we also get x right back out. If g of x is the inverse of f of x, in other words, we verified these two conditions and they both hold, they're both true, then we can also write this particular notation instead of g of x. So this reads as f inverse of x. So it looks like we have an exponent in here. This is not an exponent, it's just a superscript, but it's a superscript of -1. So f of x is the function we're starting with. Notice we're using the same letter, so it's still the letter f, but we have this additional superscript of -1 tacked on. That tells us that the function we started with was f, and the -1 indicates that the new function we found is the inverse of f. So this is just another notation for an inverse to show that two functions are related by the inverse relationship. So let's do a couple examples where we have to apply these criteria for inverses to determine whether or not two functions are inverses of one another. So here's our first example. We want to show that f of x equals x cubed minus 1 and g of x equals the cube root of x plus 1 are inverses of one another. So we have to check two compositions. We're going to take each function and plug it into the other, and if we can show that they cancel each other out, in other words, they leave us with just an x after we fully simplify, then that suffices to show that these two functions are inverses of one another. So first let's check f compose g. So if you remember, this means we're taking f and we're plugging g of x into it. We're doing this without any specific inputs. We're just doing this in the most generic situation possible. So g of x is equal to the cube root of x plus 1. So this is f of the cube root of x plus 1. So the rule tells us we take our input, we cube it, and we subtract 1. So we're going to apply that sequence of operations to this specific input. So we take this input, we cube it, and we subtract 1. Now it's just a matter of following order of operations to simplify. So we're cubing a cube root. Well, just like a square root and a square cancel, a cube root and a cube cancel. So that's just going to leave us with the x plus 1 minus 1, which simplifies down to x. So f compose g of x is equal to x, which is one of the criteria we have to meet in order to show that these two functions are inverses. So we're good for the first one. However, this isn't enough. We have to check g compose f as well. So we have to plug things in the other order. So this is g with f of x plugged into it. F of x is x cubed minus 1, so that's what we're plugging into g. So the rule for g says take our input, add 1, and then take the cube root. So we're applying that sequence of operations to this specific input, x cubed minus 1. So we need to start on the inside of the root this time. So I can combine my negative 1 and my positive 1. Those cancel. I'm just left with the cube root of x cubed. So now we're applying the same operations but in the different order. We're cubing first and then we're taking a cube root. Fortunately, order doesn't matter. So anytime we have something that's cubed and there's a cube root applied to the same piece of the problem, they're going to cancel out. So that's just going to leave us with an x. The cube and the cube root cancel. So g compose f also identically equals x. So because f compose g is equal to x and g compose f is equal to x, f of x and g of x are inverses of one another. Let's try another one. So let's show that f of x equals 2x plus 5 and g of x equals 1/2 x minus 5 are not inverses. So we're following the same criteria for checking, but we want to show using that criteria that these two functions are not inverses. So let's check f compose g of x. So we're taking g of x and we're plugging it into the rule for f. So g of x is equal to 1/2 x minus 5. So we're plugging this into f, which says take our input, multiply by 2, and add 5. So we're applying this to our specific input of 1/2 x minus 5. This is a distributive property problem at this point. So the 2 needs to distribute to the 1/2 and to the minus 5. So 2 times 1/2 is 1. That cancels out. We're just left with the x. And then 2 times negative 5 is negative 10. So we have x minus 10 plus 5. If I combine my negative 10 and my positive 5, I'm left with x minus 5. And at this point, algebraically, there's nothing else I can do to simplify anything, to combine anything. So because this is not identically equal to x, f of x and g of x are not inverses. So if there is anything left besides just an x once we do one composition, they are not inverses. Now notice we don't even have to check g compose f. If one composition doesn't work, it doesn't matter whether the other one works or not. Both have to be met in order for us to have inverses. So if even one is not met, that means the whole problem is null and void. It means the functions are not inverses of one another. So we now know how to determine whether or not two given functions are inverses. So now let's assume we have inverses. What can we say about those two functions, assuming that we know that they are inverses? So let's specifically talk about domain and range. What is actually inverting? When we talk about an inverse, we're talking about something flipping. Well, what's actually flipping? Well, the answer is the domain and range. When we have a function and its inverse, the domains, in other words, all the x's, and the ranges, all the y's, actually switch places. So this means the domain, the inputs for f of x, become the range for f inverse of x. So in other words, what we're putting into our original function now becomes what we get out of our inverse function. The domain of f of x becomes the range of f inverse of x. And then the opposite is also true. So the range of f of x becomes the domain of f inverse of x. So whatever we're getting out of our original function represents what we could put into our inverse function. So anytime we have two functions and we know their inverses, the domain of one is the range of the other, and vice versa. This becomes important in certain situations when a function has a restricted domain, and we're going to talk about this later. What happens when our function is not one-to-one? So we know one-to-one is a particular condition we need in order to have a function. Well, if a function is not one-to-one, it doesn't mean we have to just throw away the problem and say nothing works. If we can focus on the domain and what we know about domains and ranges for inverses, then potentially we can find an inverse with a little bit of a restriction on the domain. So we'll get there in a minute. So we know how to determine whether or not two functions are inverses. We know their domains and ranges are going to switch, but the one thing we haven't talked about yet is how do we actually find an inverse? So what if we're given a function and we want to find the equation of its inverse? That's what we're going to look at next. So finding the equation of the inverse from a given function. So the rule of thumb overall is opposite operations, opposite order. So if we're taking a function and we want to find its inverse, the inverse is going to have all of the canceling operations of the original function. So a multiplication will become addition, a multiplication will become a division, an addition will become a subtraction, an exponent will become a root, etc. And all of the operations are applied in the opposite order. So opposite operations, opposite order. So say, for instance, in our original function, the first thing we would simplify in order of operations is a multiplication. Well, that means in our inverse, the last operation we would simplify would be a division. So opposite operation taking place in the opposite order. Now, fortunately, it doesn't all have to be done mentally like this. We have a sequence of operations we can follow that help us to find an inverse every time. So our first step is make sure the original function f of x is one-to-one if we aren't already told so. One of the easiest ways to check this is to use a graphing calculator or some type of graphing utility and graph the function you're given. Remember, a one-to-one function has to pass the horizontal line test. So if it doesn't pass the horizontal line test, it means it's not one-to-one. It means we might need to do a little bit of extra work. So typically, most of the things we see are going to be one-to-one, but we don't want to sweep this under the rug entirely. This is something we do need to consider. Step 2, replace f of x with y if necessary. If we're given actual function notation with f of x, we want to put a y in place of f of x. The reason we want to do this is because we're about to invert. Some things are going to switch places. The f of x is going to move around. So it's helpful to write it as a y instead so that we're only moving one variable around. So step 3 is where we actually invert. This is where we're actually taking the inverse. So we switch all the x's and all the y's in the equation. So anywhere there was an x, the x becomes a y. Anywhere there was a y, the y becomes an x. And this makes sense based on what we just talked about. We talked about domain and range. Domain and range switch places. Well, domain represents x, range represents y. If they're switching places in our inverse, then in terms of our equation, this means that the x and the y are switching places in our equation. So this is the actual taking of the inverse, but we still have a little bit more work to do. Typically, we don't like to have an equation where it's x equals something. We like to have an equation where it's y equals something. So our next step is to solve for y. So we've switched x and y. Now we want to apply the sequence of operations that we need in order to get y by itself again, so to solve for y. Once we do this, we have essentially found the inverse in the standard form that we like. So we like to have y by itself, we inverted, and then we solved for y. So we have all the operations it would take to get y back by itself. We have an inverse that's something we could graph, something we can use, something we can rewrite in function notation. So our final step is once we've solved for our inverse, we want to replace y with our notation for an inverse, which was f inverse of x, f with a superscript of -1. And we can always check our work by using this opposite operations, opposite order idea. So all of the operations in our original function should be represented in our inverse, just opposite. So an addition becomes a subtraction, a multiplication becomes a division, etc. And all of the opposite operations should occur in the opposite order. So whatever happened first in the original function, we should have the opposite operation happening at the end of the inverse function. Let's start with a simple example. So we want to find the inverse, and then we want to find the domain and range for the original function and for the inverse. So our function is f of x is equal to 2x plus 5. So this is a linear function. If you imagine what this would graph like, it'll have a y-intercept of 5 and a slope of 2. So it's a diagonal line that passes through the y-axis at 5 and has a slope of 2. So you can already start thinking about domain and range from a sense of the picture. But in terms of domain and range for the inverse, we don't know until we know what the inverse is. So let's start by replacing f of x with y. So y is equal to 2x plus 5. Remember, f of x and y mean the same thing. So wherever there's an f of x, we can always substitute with a y. Now we're going to take the inverse. So inverting means switching x and y. So wherever there's a y, it becomes an x. Wherever there's an x, it becomes a y. So we now have x is equal to 2y plus 5. So for all intensive purposes, we have taken the inverse at this point. However, in terms of understanding what we actually have and potentially being able to graph something, we don't really know how to graph from an x equals standpoint. We only know how to graph from a y equals standpoint. So even though we've taken the inverse, we now need to get y by itself so that we can understand what this looks like, what's really going on a little bit better. So y is multiplied by 2, and we've added a 5. So first thing I need to do is move the 5 over. So subtract 5 from both sides. I have x minus 5 is equal to 2y. Now I need to divide out the 2. So x minus 5 divided by 2 is equal to y. So now that y is by itself, we have officially solved for our inverse function. So f inverse of x, we replace y with our new notation, is equal to x minus 5 divided by 2. So this is the inverse of our original function, which was f of x equals 2x plus 5. So let's see if we can apply that opposite operations, opposite order rule here. Let's see if this actually applies here. So in our original function, imagine taking a number and plugging it into the function. So say we wanted to take f of 1. We wanted to figure out what that is. Let's follow the sequence of order of operations and think about what would we simplify first. So if I were to plug in a number in place of x, first thing I would need to simplify is the 2. I would have to multiply by 2. So the first operation is multiplication by 2. That means when we go to the inverse, the last operation, so opposite order, has to be the inverse operation of multiplying by 2. So the opposite of multiplying by 2 is dividing by 2. So in our inverse function, notice the last thing we would do to simplify something would be a division by 2. So multiplication is canceled by division. Multiplication occurs first in our original function. So the opposite operation, division, occurs last in our inverse function. And then the next operation in our original function is addition by 5. So to cancel out an addition by 5, we subtract. So the last operation in our original function is addition of 5, which means the first operation in our inverse is subtraction by 5. So take some time, think about this, see if you can wrap your mind around it. This is not essential to be able to figure out what an inverse is, but it's helpful as a way to sort of check your work and think through whether or not your answer makes sense. So we've got our function, we've got our inverse. Now let's talk about domain and range. So the domain of our original function, our linear function, let's think about that. Well, remember, in function notation, anytime we have an equation, we have two situations where there's a restriction in the domain. So we assume the domain is all real numbers, and then we take into account those possible restrictions. So the only restrictions we have are for dividing by 0. If there's a denominator, we have to make sure we don't divide by 0. And anytime we have something like a square root. So we have to make sure we're not taking a square root of a negative number. Well, there's neither a denominator nor a root in this particular function, which means the domain is all real numbers. Well, if the domain of our original function is all real numbers, that means the range of our inverse function is all real numbers. Now, in theory, we could figure out the range of our original function, but believe it or not, we haven't talked about range all that much in this class. That's because determining range is not an easy thing to do. There's no clear-cut set of criteria like we have for domain. We know how to figure out what a domain is with only a couple rules. Well, unfortunately, there's no rule like that for range. So instead, if we can find the domain of the inverse, then that will give us the range of the original function. So in most situations, we're going to find both domains by applying those rules we know, and then we use the domains to find the ranges. So let's look at our inverse. It's x minus 5 over 2. It may not look like it, but this is actually a linear function as well. So if we were to distribute that division by 2 to both terms, we would have a 1/2 in front of the x, and then the y-intercept would be negative 5 over 2. So even though there is a denominator, there's no way this denominator could be 0. So we don't ever have to worry about dividing by 0 here. There's no square root, nothing like that. So that means our domain is all real numbers. We can plug in anything we want and this expression is going to be defined. So if our domain for our inverse is all real numbers, that means our range for our original function is also all real numbers. So again, just to reiterate, in any situation, we have rules for determining the domain. We don't have rules necessarily for determining the range. So if we can determine the range of the original function, it's going to be the domain of the inverse. Domain of the original function is going to be the range of the inverse. We use our domain rules. That gives us both of our ranges. They change places. Let's try another example. So same directions, we want to find the inverse and then find the domain and range for the function and the inverse. And our new function is f of x is equal to x minus 2 cubed. Okay, so we replace our f of x with a y. Then we take the inverse. So we switch our x and we switch our y. So we now have x is equal to y minus 2 cubed. So now we need to solve for y, which is 9 out of 10 times going to be the hardest part of the problem anyway. So y has a subtraction of 2, but it's also cubed. Notice the cube is on the outside of everything. So that's the first thing we need to get rid of. We need to get rid of that exponent first. So to cancel a cube, an exponent of 3, we have to take the cube root of both sides. So we take the cube root, that now becomes the cube root of x, and then it cancels on the right-hand side, and we're just left with the y minus 2. We still need to get rid of the subtraction, so we need to add 2 to both sides. So this now becomes the cube root of x plus 2 is equal to y. Once y is by itself, we have officially found our inverse, so we change our notation to indicate that this particular function, this rule, is the inverse of our original function. So f inverse of x in this case is equal to the cube root of x plus 2. Okay, now let's talk about our domain and range. So we have our two functions. We want to find the domain and range for each. For our original function, there's no denominator. There's no root, so there's no way we could have anything that's undefined. So our domain is all real numbers. That means that the range of our inverse is also all real numbers. Now for our inverse, we want to determine the domain of the inverse. There is a root in this problem. However, you can take a cube root, or specifically any odd root, of any number you want. We can't take a square root of a negative because there's no way we can multiply a number by itself and get a negative number. However, we can take a cube root of positive numbers. We can take the cube root of negative numbers. It's defined for any number we want. So again, just to reiterate, even roots, we have to worry about that negative issue. If it's an odd root, we don't have to worry about that. We can take odd roots of any type of number we want. So in this case, the domain is also all real numbers. This is defined for any real number, which means the range of our original function is also all real numbers. Now let's try an example with slightly more exotic looking algebra. So same directions, and our function is f of x is equal to 2x plus 3 over x minus 4, where x is not equal to 4. So we put that stipulation on it just to make sure we're not dividing by 0. So if we were to plug in a 4, the denominator would be 4 minus 4, which is 0, which is undefined. So we put that stipulation on there to make sure we're taking into account domain. So we'll worry about that in a minute when we start talking about the function, its inverse, and domain and range. So first thing we need to do is find our inverse. So replace f of x with y, and then we invert. So we switch the x's and switch the y's. So notice in this problem, we actually have two x's on the right-hand side of the equation. That means both of those x's are going to become y's. So we now have x is equal to 2y plus 3 over y minus 4. Now we need to solve for y. So ultimately, that's always the goal. Once we invert, we need to solve for y. The problem, however, is that we have two y's on the right-hand side. So getting y by itself is not as easy as just moving some numbers around, maybe subtracting, maybe dividing. It's not that simple here. We have two y's. We have to take that into account. So what we need to do first, we have something with a denominator. Ideally, we need to get rid of the denominator. That's going to be a good start for us. So if we multiply both sides by the y minus 4, then we can eliminate the denominator and make our lives a little bit easier. So let's move over that y minus 4. So we have x times y minus 4, and then the denominator goes away on the right-hand side. Well, intuition should tell you now, okay, I need to distribute. That's correct. We need to distribute this x to the y minus 4. So we have xy minus 4x is equal to 2y plus 3. So anytime we have any type of problem where we're trying to solve for a variable, but variables are on both sides, the general strategy is called combining like terms. So if y is what we're trying to solve for, then ideally we need to try to get all the y's on one side of the equation so we can combine them and isolate the y. So I have y's on both sides right now. I have an xy on the left and a 2y on the right. So one good strategy at this point is to move all our y's to one side. So let's move the 2y over to the left, and then because that 4x doesn't have any y's in it, let's move that to the right. So we're subtracting the 2y and we're adding the 4x. So if we combine both those operations into one step, we get xy minus 2y is equal to positive 4x plus 3. If you need to take a break, pause the video, do that in 2 steps. You don't have to do it in 1, you can do it in 2 steps. Make sure you get to this point and it makes sense for you. Okay, so xy minus 2y, ideally we'd like to be able to combine that, but the x and the 2 are different. We can't combine them into one term. However, notice that both of the terms on the left have a y in common. It's called a common factor. They have something that's multiplied in each term that's common to both of them. This is, in this case, the greatest common factor. Hopefully that term jogs your memory a little bit. If you remember, whenever we have something in common between two terms, we can factor it out. So it's like dividing it out but rewriting it as a multiplication. It's pulling it out front and then keeping what we have left. So we have a common factor of y in both of the terms on the left. We can factor it out, and we're left with an x minus 2, and then all of that is equal to 4x plus 3. So just to reiterate, our goal is to solve for y. We want to get y by itself. Well, notice at this point it's y, and it's multiplied by a cluster of things. It's multiplied by x minus 2. So if we were to divide out at this point what it's multiplied by, then y will be by itself. So divide both sides by x minus 2, and we get y is equal to 4x plus 3 divided by x minus 2. Y is by itself, everything else is on the other side. There's only one y in the problem at this point, so this is our inverse. We officially solved for our inverse. So we change our notation. F inverse of x is equal to 4x plus 3 divided by x minus 2. Now let's look at our domain and range. So we've got our function, we've got our inverse, we want the domain and range for each of them. So these are rational functions with something other than a constant in the denominator. So we do have to take into account what would make us divide by 0. In our original function, the denominator is x minus 4. So the value of x that would make us divide by 0 is 4. Now keep in mind, we mentioned this before, but just so we're clear, whatever happens in the numerator doesn't matter. It doesn't change anything. If the numerator is 0, the whole thing is 0, which is defined. It's okay to have something equal to 0. However, if the denominator is 0, we're dividing by 0, which is not allowed. So we don't care about the numerator in this instance, we just care about the denominator. So if x is 4, the denominator becomes 0, and that's a problem. So our domain is everything except 4. So we take all real numbers and we split it up into two intervals around the number 4, around the number we're excluding. So our domain is negative infinity to 4, union 4 to infinity. So it's all real numbers except the number 4. It's split up around that number 4. So that means the range of our inverse is the same thing, negative infinity to 4, union 4 to infinity. Okay, now what about the domain of our inverse? Same situation, we have a rational function. It's a different rational function, but we run into the same kind of problem. We have to make sure we don't divide by 0. In this case, the number that would make our denominator 0 is 2. So 2 is what we have to exclude. So our domain is all real numbers except 2. So it looks basically the same in form, but now we're excluding the number 2 instead of the number 4. So the domain for the inverse is negative infinity to 2, union 2 to infinity, which means our range for our original function is also the same thing. So this is the first problem we looked at where domain and range weren't really just negligible. We really had to take into account what one was in order to figure out the others. Now we're going to take that one step further, and we're going to look at a situation where domain and range become critical to the entire problem. So it's not going to be just determining the domain and range at the end. We're going to have to take them into account throughout the whole problem. So let's try this one. Same directions. Our new function is f of x is equal to x squared minus 1, where x is less than or equal to 0. So what does this little bit tacked on the end have to do with anything? Well, we'll get there. F of x, change it to a y, first step, standard first step. Now let's take a minute and let's think about what the graph of this looks like. So y equals x squared minus 1. Well, that's quadratic. We talked about graphing quadratics, but this one's even simpler than that. So this one can be directly related to the parent function. So our parent quadratic function, that's a parabola centered at the origin, and we're subtracting 1, which means we're shifting our graph down 1 unit. So this is what our graph looks like. It's a parabola shifted down 1 unit. Now, what's the problem with this graph? The problem is that it is not one-to-one. It doesn't pass the horizontal line test. So based on how we've defined functions, our requirement is that we're starting with something that's one-to-one. Well, this function is not one-to-one. It fails the horizontal line test. This is where that x less than or equal to 0 comes in. So this was part of the problem. This was supplied to us. We were told we only want to take x less than or equal to 0. What that means is that we're only keeping part of the graph. We're only keeping the portion of the graph for which our x values are less than or equal to 0. Notice if we only keep that half and we throw away the right-hand portion of the graph, what we're keeping is now one-to-one. It now passes the horizontal line test. This is okay to do. The reason we're allowed to do something like this is because we're not really throwing anything away that we needed, in the sense that we're not throwing anything away that gave us a unique y value. Notice if we just keep this half of the graph, we have every single possible y value for our function. If we kept the right half as well, we'd be getting duplicate y values, duplicate function values. So although we'd have the whole picture, we aren't getting any extra information necessarily about the function. So they've specifically told us we only want to keep the half of this graph that corresponds to negative x values. So that's our general situation we're in. We're throwing away half of a graph, we're keeping the other half so that what we're defining is actually one-to-one, so that we can actually find the inverse. Okay, so let's get back to inverting. So we replaced our f of x with a y. Now we need to switch our y and our x. So on the right-hand side, again, there are two x's. Both of those need to become y's. So this now becomes x is equal to y squared minus 1, where y is less than or equal to 0. So hang on to this part. Don't forget about it, the y less than or equal to 0. But let's just worry about the algebra to get y by itself first. So we've got that y squared minus 1. We want to get y by itself. So add the 1, move that over. So x plus 1 is equal to y squared. Now we need to take the square root to get rid of the square. But remember, when we take the square root in an equation, we have to put the plus minus on there to show that if we were to backtrack, both a positive and a negative, if we squared them, would take us back where we came from. So we have to put a plus minus there. Now the problem with something like this is not actually a function, believe it or not. It's not immediately obvious, but imagine plugging in an x value. Say we plugged in 1. So 1 plus 1 is 2, so we'd have the square root of 2. However, that plus minus, that tells us we could have a positive 2 or a negative 2. That means for this specific x value we plugged in, we could actually get out 2 possible outputs. Well, that is, by definition, not a function. Anytime we could plug in an input and get 2 different outputs from it, it's not a function. So what we've found so far, although we didn't break any algebraic rules, it's not a function. So what do? Well, this is where that y less than or equal to 0 comes into play. So we only want the part of our particular rule that corresponds to negative y values. We want y to specifically be less than or equal to 0. That means we're only going to keep the negative. We keep the negative of the square root of x plus 1 because that's going to give us the y values that are less than or equal to 0. If we keep the positive, we're getting positive outputs. If we keep the negative, we're getting only the negative outputs, the ones that we want. So our actual inverse is going to be y is equal to negative square root of x plus 1. So I change to my function notation. F inverse of x is equal to negative square root of x plus 1. Now let's talk about our domain and range. So here's our original function. Here's our inverse. We want the domain and range for each of them. This one is definitely not throwaway, so we're really going to have to pay attention to what's happening here. So in our original function, remember, our original function has an actual domain of all real numbers, but we decided if we keep the entire domain, we have something that's not one-to-one. Well, if it's not one-to-one, we can't define an inverse. So we threw away half of the graph, and we only kept one half of it that gave us all the possible outputs we could get, but didn't have any repeated outputs. The way we decided which piece we wanted is because we had that extra little piece of information that said x has to be less than or equal to 0. X less than or equal to 0 is actually our domain. It tells us the x values we want to keep as possible inputs for our function. So all we need to do now is translate that inequality, x less than or equal to 0, into interval notation. So that is all the numbers from negative infinity to 0. So in interval notation, that's negative infinity, comma 0. Always parentheses with infinity, and then a bracket with 0. So that is our domain. Specifically, it was restricted, so we could make this function one-to-one, so we could find the inverse. So that means the range of our inverse function is going to be the same thing, negative infinity to 0. Now what about our inverse function? So we did everything we needed to do. We knew we kept the negative because we wanted y to be less than or equal to 0. We threw away the positive. That way what we have is a function. Okay, so we have a square root. We know we can't have anything negative under the square root. So that means that x plus 1 has to be greater than or equal to 0. If it's less than 0, then it's undefined. We can't graph it. It doesn't exist on our coordinate plane. So this means x has to be greater than or equal to negative 1. Anything bigger than negative 1 is okay. We can take the square root of it. Anything less than negative 1, if we plug into our square root, we end up with something that's undefined. So we only want to keep x values that are greater than or equal to negative 1. So as an interval, that is negative 1 to infinity. That is our domain. We can plug in anything greater than negative 1. We can't plug in anything less than negative 1. So that means our range for our original function is also negative 1 to infinity. And this actually makes sense based on our graph. So remember, we graphed this, and it was with the parabola, starting with the quadratic parent function, shifted down 1 unit. So our range corresponds to our y values. If we were to project our graph onto the y-axis, we have everything from negative 1 up to infinity. So all the algebra corresponds with the graph as well. Everything works together. Let's try one final example. So same directions. Our new function is f of x is equal to the square root of x plus 5. So immediately, this reminds me of the previous one. With the previous one, we started with something quadratic, and our inverse was a square root. Well, now we're starting with a square root. So let's see what happens when we start with this one, and we want to find the inverse of this particular function. So convert to y. Y is equal to the square root of x plus 5. Let's graph this one. So this is the square root parent function, and adding on the 5 to the x is a horizontal shift. Remember, x always does the opposite, so that means we're going to shift to the left 5 units. So here's our graph. So this is one-to-one. We don't have an issue with the domain here because this passes the horizontal line test. So we don't have to worry about that. So let's just continue on from there. So we invert our x and y. So we have x is equal to the square root of y plus 5. We need to get the y by itself, so we need to square both sides to get rid of the square root. So we have x squared is equal to y plus 5. Now we subtract our 5 and move it over. So we have x squared minus 5 is equal to y. So that's our inverse, right? For all intents and purposes, algebraically speaking, that's our inverse. So we rewrite it as f inverse of x is equal to x squared minus 5. Okay, now let's graph this one. If we were to graph this particular equation, this is quadratic, so it's the quadratic parent function shifted down 5 units. So here's our graph. However, this is not one-to-one. So we didn't talk about it too much, but a function and its inverse should both be one-to-one. If they're inverses of each other, then that means if we start with one, we'll get the other. If we start with the inverse and we're to try to find the inverse of that, we would get back to the one we started with. So that means both a function and its inverse have to be one-to-one for the whole situation to work out. Well, this inverse, as we defined it, is not one-to-one. So what are we going to have to do? What do we need to do to figure this out? Well, let's go look at the domain and range, and then maybe that'll give us some more information about how we can fix this problem so that our inverse is one-to-one. So we found our function and our inverse algebraically. We're good there. We want the domain and range. So for our original function, we know we have a square root. The square root has to be greater than or equal to 0, so x plus 5 has to be greater than or equal to 0, which means x has to be greater than or equal to negative 5. So our domain is everything from negative 5 to infinity, which means the range of our inverse function is also negative 5 to infinity. And that also corresponds to what we just saw on the graph. The y values go from negative 5 up to positive infinity. Okay, now, in theory, we want to find the domain of our inverse function. And as it stands, the domain should be all real numbers. We don't have any way to divide by 0. We don't have any way to take a square root of a negative. However, we just decided based on the graph that that's a problem. If we keep all real numbers, our function is not actually going to be one-to-one. That's a problem. If it's not one-to-one, then this whole problem doesn't work out the way we need it to. So instead of solving for the domain of this particular function of the inverse, let's see if we can just manually figure out the range of the original function. So if we can figure out the range of the original function, domain and range are always compared to one another. They're always the same. So regardless of which one we can figure out the other directly from that. So let's see if we can figure out the range of the original one. Well, the good news is we already graphed it. So if you think about what the graph looked like, you can figure out the range from that. So this was the square root parent function shifted 5 units to the left. Well, remember from the graph, to find the range, we project everything onto the y-axis and we determine how much of the y-axis does it cover. Well, the specific thing we're interested in here is the fact that the range doesn't drop below 0. When we're taking the square root of a number, we never get anything less than 0. We can get any positive number, anything bigger than 0. We just can't get anything less than 0. So the range of our original function is 0 to infinity. It's all the positive numbers from 0 to infinity. So that means the domain of our inverse is also 0 to infinity. It has to be 0 to infinity. So let's recap. So the inverse, just as it stands by itself, if we were to graph it as its own thing, its domain would be all real numbers. But we're saying the domain is only 0 to infinity in order for this inverse relationship to work out the way it needs to. So what we're going to have to do is we're going to have to add a restriction onto our inverse. Just like with the last problem, we were given a restriction to start with, and we had to apply that and propagate it throughout our problem. Now we have to add a restriction on. We have to say that, okay, the domain of this function as it stands is all real numbers, But because we're defining it as an inverse, we can't keep all of that. We can only keep the portion from 0 to infinity so that everything works out the way it needs to. So we're going to add on the restriction x is greater than or equal to 0. The reason we're doing this is so that the domain of our inverse matches up with the range of our original function. So if we're starting with a square root and we want to find an inverse, we're automatically going to have a restriction on the domain telling us what portion we want to keep so that what we define is 1 to 1. If we're starting with a square root and we find the inverse, which in this case is quadratic, we're going to have to put the restriction on there ourselves, again, so the domain and range match up the way they're supposed to. So these two last problems are really special cases of the inverse situation. Most problems where you're solving for an inverse, domain and range don't become an issue. It's pretty straightforward. If you can wrap your mind around these two, then you can pretty much deal with any inverse problem you want. So let's wrap it up by talking about how we find an inverse from a graph. So suppose we're not given actual function notation. Maybe we're just given a graph of a function. Well, how do we find the graph of the inverse? The graphs of a function and its inverse are mirror images across the line y equals x, which is the 45-degree diagonal. So if you remember, this is the identity parent function. It's that diagonal line with a slope of 1 that goes directly through the origin. So it's 45 degrees up from the x-axis. So remember, for a function and its inverse, the domains and ranges switch places. So the domain of the function is the range of the inverse. The range of the function is the domain of the inverse. Well, all domain and range represent is x and y. They represent x and y in an equation, so they also represent x and y on the graph. So if they switch places, then from a graphing standpoint, this means that all the x's and all the y's in our coordinates switch places. So if a point is on the original function, it has a coordinate of x and y, then the corresponding point on the inverse is going to have the same coordinates, but they're going to be flipped. So the x is going to become a y, and the y is going to become an x. So you can visualize what an inverse looks like by using this mirror image idea, but realistically, it's more practical just to pick a couple points. So to aid in graphing, we're going to pick a couple points from the original function, and then we're going to actually flip the x and y to find the corresponding points on the inverse. So let's look at an example. So we've been given a graph of a function and we want to sketch the graph of the inverse on the same coordinate plane. So here's our function. It's a linear function. So as opposed to just trying to visualize what a mirror image looks like, it's not as easy as just flipping across y or x. We're flipping across a diagonal line. One good option is to pick a couple of points on the graph and then flip the points themselves. Typically, the easiest points to identify are going to be the intercepts. So we have one x-intercept and one y-intercept. So let's highlight those. Those are the points we're going to use to invert and graph the inverse. So we have the point 40 and the point 02. So on the inverse, the point 40 becomes the point 04. The 4 and the 0 switch places. So the x becomes a y, the y becomes an x. And then 02 is going to become 20. So we put those on our graph, and then the shape is going to be the same. So the inverse and the original function have essentially the same shape, just reflected across this diagonal line. So the original shape is a diagonal. So this is also going to be a diagonal, just intersecting these new points that we got from inverting our x's and y's. Let's try one more. So here's our graph. We want to sketch the inverse. We can do it the same way though. Identify our intercepts. So our x-intercept is -4 and our y-intercept is 2. So to find the corresponding points on our inverse, we invert the coordinates. So it becomes 0, -4. Notice I didn't change the sign. I just changed which one was x and which one was y. And then 02 becomes 20. So I put those on my graph. This is a square root graph, so when I'm graphing the inverse, I'm also graphing something that looks like a square root, just passing through these particular points. So I connect my dots, staying consistent with the shape of the original graph, and this is the graph of our inverse. So when we talk about domain and range switching places, that means a lot of different things, but essentially it boils down to whatever was an x becomes a y, whatever was a y becomes an x. For a graph, that means switching coordinates. For an equation, that means actually switching the variables. So let's sum up what we've talked about. So two functions, f of x and g of x, are considered to be inverses if two criteria hold. So f composed g of x is identically equal to x, and then also g composed f of x is identically equal to x. So in other words, if we take one function and plug it into the other one, they cancel each other out and we're just left with the variable. Now keep in mind, both of these criteria have to hold for our functions to be inverses. It's possible that one composition could work and the other might fail. Both have to work in order for our functions to be inverses, so they have to be able to cancel each other out regardless of which one we apply in which order. So if we want to determine whether functions are inverses, we apply these two criteria. But if we're given a function and we just want to find the inverse, we take f of x and replace it with y if it's not already written in y notation. And then we invert by switching x and y. So anytime we're taking a function and inverting, that essentially means that all the domains and all the ranges switch places. So practically speaking, from an equation standpoint, that means x, which represents the domain, switches places with y, which represents the range. Then we need to solve for y. So we want to get it into a form that's more workable for us. Inverting is switching x and y, but solving for y again is what makes it useful for our purposes. Once we solve for y, we replace y with f inverse of x. Once y is by itself, we have essentially solved for the inverse. So what we found is a set of rules that feature the opposite operations in the opposite order from what we had in our original function. And then for a couple of special situations when the function or its inverse isn't one-to-one, remember those situations where we started with a quadratic or we started with a square root, we may need to place a restriction on one of the domains. So if we can cut off a portion of the function that keeps it from being one-to-one, then we can take the inverse just like we did following the same instructions.